Next talk is, I don't know how to pronounce this, but I'm going to take a stab.
My name is Ruofei, or you can
Ruofei.
call me Soares. It's my nickname.
Ruofei or Soares, great, thank you. And I think he's going to be talking about Ferrite, which was developed with Stephanie Balzer. So I've got a few fun facts. Ferrite was used in Servo's Canvas implementation, I think, or at least experimentally.
It's an experimental.
Okay.
So it's not much.
One of them you already gave away, which was that I discovered you have two names on the internet. And Stephanie and I did our PhDs together. Good times. All right, so I'm going to unshare, and Ruofei, you can take it over.
Thank you. So I'll try to share my screen. So right now, let's see if I can share my screen. Yes, I've pre-recorded my video, and so I pre-recorded my presentation as a video, and I'll just play it. So anytime, feel free to interrupt if you have any question. By the way, I'm not sure if I have. Let me just try to share again, because I think there's an option for sharing the sound. Yes. Okay. Hello, everyone. Today, I will be presenting about Ferrite, a session types DSL we have developed for Rust. My name is Ruofei, a software engineer and an independent researcher. And this is a joint collaboration work with Stephanie Balzer from CMU. In this talk, I will first talk about the challenges of enforcing protocol adherence using regular Rust channels. We will then look at how session types can be used to solve these problems and how they are implemented in Ferrite. We will also look at how we can use Ferrite and session types in practice using Servo as a practical example. Now we know that real-world applications tend to be complex. A program would not only need to perform some local computations, but also have the need to communicate with other programs. The same can also apply to a piece of code inside a program, which may be running concurrently with other code and need some ways to communicate. In the simplest case, we can consider the scenario of a client program sending one or more messages to a provider. There are many ways we can implement such a communication pattern. For instance, using message passing concurrency. In Rust, the most common approach is to use a channel library to create a sender and receiver endpoints that are linked, and have the client and provider components hold each side of the endpoints. The use of channels are preferred over alternative approaches, such as shared memory, as channels are more robust and simpler to use. However, in terms of expressiveness, Rust channels have the limitation that communication can only be done in one direction, and that the payload type is fixed. This limitation in Rust channels can make it more challenging to implement more complex communication protocols. For example, we may want to have a request-response protocol where the client sends a message and expects a reply from the provider. The communication can also go both ways multiple times, and the message types may change based on the state of the client and the provider. In practice, it is also common to have scenarios such as multiple clients needing to communicate with a single shared provider. In such case, the shared provider will have to protect its state from becoming corrupted, which can be caused by concurrent modification when multiple shared communications happen in parallel. While it is more challenging to implement and enforce communication protocols in Rust channels, we can instead use session types to create a more precise specification of these protocols and enforce protocol adherence inside the program implementation itself. To illustrate the difference, we will use Servo as a practical example of how real-world protocols are encoded in both Rust channels and session types. Servo is an experimental browser engine developed by Mozilla, and as a web browser, there are many components in Servo that run concurrently and communicate through Rust channels. For our use case, we will focus on the canvas component, which implements the rendering of 2D canvases in web applications. As an example, the link on this slide shows a demo web page that draws colorful circles on the HTML canvas. The canvas component in Servo is implemented as a canvas pane thread, and it is shared among multiple client components. For instance, a JavaScript client from a web application may instruct the canvas pane thread to perform some drawing operations. At the same time, the display component would request the image bitmap information from the canvas pane thread to display them on the screen. We now look at how Servo defines the canvas payload types for communication through Rust channels. At the high level, Servo defines the constellation canvas message type for creating new canvases and a separate canvas message type for performing drawing operations on a specific canvas. Inside the create submessage, there is an ID sender field which contains a sender endpoint for the canvas pane thread to send back the ID of the newly created canvas to the client. This technique is commonly used as a workaround to support bidirectional communication in Rust channels where the client expects a result to be sent back from the provider. Next, in constellation canvas message, there is also an explicit exit submessage, which instructs the canvas pane thread to shut down and stop processing any further message. In the canvas message enum, the submessage types such as canvas 2D and from layout requires a canvas ID to be specified alongside the message so that the canvas pane thread knows which canvas to operate on. And finally, there is also an explicit close message for removing a specific canvas by the ID provided. In the implementation of the canvas pane thread, the underlying canvas objects are stored in a hash map, indexed by the canvas ID. The component defines a helper function called canvas, which retrieves the underlying canvases from the hash map and asserts that the canvas data is present. Should an invalid ID is provided, a panic will be raised and cause the component to crash. Finally, there is a start function to start the canvas component in a separate thread and returns the sender endpoints of constellation canvas message and canvas message to the clients to communicate through the provided Rust channels. From the design of the canvas message types, we can see that there are several flaws that can potentially introduce protocol violations. As we have seen previously, if a client sends an invalid ID to the canvas provider, it can cause panics to be raised in the provider and crash the component. This may happen more commonly than we expect, as a client may accidentally send message to a canvas that have been previously closed, which would have invalidated the canvas ID. Other than that, if the exit message in constellation canvas message is called, all subsequent messages sent to the canvas pane thread will be dropped, and this will in turn cause panics on the clients. With Rust channels, we also need to have an ad hoc embedding of sender inside the message types to encode bidirectional protocols such as the create message. Furthermore, the encoding of bidirectional protocols does not enforce that the provider must in fact send back the result to the client through the provider sender. As Rust has an affine type system, the silent dropping of a sender variable is allowed, causing no result to be sent back. Unfortunately, the use of bidirectional protocols can be quite common in practice. When we look inside the submessage types, canvas 2D and from layout message, we can also see the endpoints being embedded in several places. The submessages send data and get transformed, for example, does not have any subfields other than the sender endpoints for the client to request a result back from the provider. In fact, during our study of the Servo codebase, we are able to uncover a protocol violation in the provider implementation of from layout message, which the canvas pin thread does not send back any canvas image data result to the client in one of its nested match arms. Now that we have seen the problems of using Rust channels for communication protocols, we will see how session types can help us define more precise protocol specification. Session types allow communication to be done in multiple steps, and in each step, the communication can be done in either direction. Compared to the affine types in Rust, session types are linear, as in channels must be fully consumed by both the client and the provider. The most basic session type we have is epsilon, which represents a provider that is terminating. Following that, we have the receive and send value constructs as denoted by the right and left triangles for receiving value from the provider or sending value to it, respectively. Similarly, we have the session types for sending and receiving channels as denoted by the lolly and tensor operators. With the linear property of session types, we also have two variants of sum types, which are the internal choice for choice selection determined by the provider, and external choice, where the client determines the selection. In addition to the basic constructs, we also extend the type system with shared session types to allow a linear provider to be shared among multiple clients. The shared session types introduce two new modalities, linear to shared and shared to linear, as denoted by the notation up arrow ls and down arrow sl, to express the semantics of acquiring and releasing the linear section of a shared provider. More information on shared session types can also be found on the paper Manifest Sharing with Session Types. To get an idea of how session types can be used, let's look at how the Canvas protocol that we have discussed earlier can be encoded into session types. The first thing to notice is that in session types, we no longer need to specify the Canvas ID when performing Canvas operations. Instead, we can use separate shared channels for each canvas created. Shared session types also does not allow explicit termination, and instead takes care of shutting down the provider when all references to the shared channel are dropped. To define a shared session type, we use the linear to shared modality to indicate that we want to allow multiple clients to access the linear critical section that follows. After a shared canvas is acquired, the protocol gives the client an external choice for it to select from multiple branches. Here we show two of the example branches, with the first branch labeled message used for sending simple messages that do not require a response from the provider. Following that, the from layout branch allows the provider to send back an optional canvas image data result to the client. Notice that in each of the branch, the final session type is always the shared to linear operator, followed by a recursion back to the Canvas protocol itself. This represents the provider being released from the critical section, which it can then be used to continue serving other clients under the same Canvas protocol. Similarly, the constellation canvas message can be defined as a separate session type. Since the exit operation also becomes implicit, the session type is used only for creating new canvases. We use the right triangle operator for receiving the size and anti-alias parameters for the canvas creation. Following that, we use the left triangle operator for sending the created canvas as a shared channel back to the client. Notice that compared to the original formulation of shared session types, Ferrite treats shared channels as regular Rust values that can be cloned, so that they can be sent and be used as regular Rust values. Although there can be clear benefits of using session types for protocol specification, there remains many challenges of how we can actually implement session types and enforce linearity in a host language like Rust. For the remaining of this presentation, I will talk about our library Ferrite, which implements session types as an embedded DSL in Rust. Compared to previous approaches in Rust, Ferrite overcomes various implementation challenges and is able to enforce protocol adherence at compile time. In addition to linear session types, Ferrite also supports shared session types, which makes it practical to use session types in a shared setting. For evaluation purpose, we have also re-implemented the communication layer of the canvas component in Servo to use Ferrite for shared communication. The Ferrite library is open source and is available on GitHub. It is also published as the Ferrite-session crate. To see Ferrite in action, we first look at how the session types are encoded as Rust types. As we can see, most of the encodings are pretty straightforward. For example, the notation tau right triangle A is encoded as the Rust type receive value angle bracket T, A for receiving a value of type T and then continue as session type A. For the case of internal and external choices, we use the hlist macro to encode a type level list of session types to represent the choices available. To show an example, we have a hello world session type that is first expressed in pure session types and then transformed into Rust types. It is self-explanatory from the type signature that the session types we have defined allows a provider to first receive a string value from the client and then terminates. We now look at how a provider of the hello protocol can be implemented. In Rust, a Ferrite program offering a session type A have the Rust type session angle bracket A. So our hello provider has the Rust type session angle bracket receive value angle bracket string, n. In the body of the provider, we use the receive underscore value construct for receiving a value from the client. Ferrite expressions are written in continuation parsing style. So the receive underscore value construct takes a continuation closure, which is then given the receive string as an argument. Following that, our provider simply prints the receive string and then terminates the program using the terminate construct. The hello provider program that we have implemented earlier is required to follow the protocol specified in the session type. If we were to implement the provider incorrectly, such as trying to terminate before receiving the value, we will get a type error and the Rust program will fail to compile. The details of the error message is not too important at this point, but the key is that we get a type mismatch error saying that the provider is offering the session type n instead of the expected session type receive value angle bracket string, n. Compared to other session type libraries, Ferrite is also based on the intuitionistic formulation of session types, which does not require the dualization of session types. This means that for each session type, there are two typing rules that defines how the session type can be used from the perspective of the provider or the client. The session types are always named after the behavior from the provider perspective, while from the client perspective, the behavior is inverted. As an example, for the case of the right triangle operator, from the provider perspective, the program is expected to receive a value from the offered channel. On the other hand, from the client perspective, the program is supposed to send a value to the specified channel in the linear context. With the intuitionistic formulation, the way we implement the hello client requires it to first receive a channel of the hello session type that is offered by the provider. We can think of this being similar to defining a function in Rust. The full session type offered by the client starts with the receive channel type, and then followed by the hello protocol receive value angle bracket string, n, and then followed by n. This means that the client would receive the channel and then finish interacting with the provider before it terminates. In the body of the client, we use the receive underscore channel expression to receive the channel which is then bound to the Rust variable A in the continuation closure. The receive channel is linear, and the client must fully use it before it can terminate. So first, it sends a string value to the provider through the channel A, and then it waits for the provider to terminate via the same channel A, and then finally terminating itself. Similar to the provider, the hello client must linearly use up the channel that it has received from using receive_channel. If we violate the protocol, such as dropping the receive channel and then terminate immediately, we will instead get a type error as shown. Ferrite keeps track of the linear context at the type level when a client receives a channel using the receive_channel construct. If the client tries to terminate before the linear context becomes empty, the error message would indicate that there is still one active channel in the linear context, and therefore it cannot terminate before then. While the earlier examples may seem a little magical, we will now take a quick look at how Ferrite actually enforces linearity and protocol adherence of Ferrite programs. The key data structure in our implementation is the partial session struct, which is encoded from a formal typing judgment following the typing rules of session types. On the left, the typing judgment states that under the structural context gamma and the linear context delta, a given expression expr offers the session type A. When translated to Rust, this becomes the typing rule that a Rust expression expr would have the Rust type partial session angle bracket C, A. The Rust type C corresponds to the linear context delta, and the Rust type A corresponds to the offered session type A. The structural context gamma is left out in the encoding, as we delegate to Rust itself to handle the structural values as regular Rust variables. In Ferrite, the Rust types representing session types would have the protocol trait implemented. Following that, the linear context is represented as a type level list of session types, and it implements the context trait. The partial session struct is then parameterized by the linear context C and the session type A, with the underlying guarantee that all channels in the linear context are consumed linearly. Finally, the type session angle bracket A is actually defined as a type alias to the type partial session angle bracket open close bracket A, indicating that it is a top-level Ferrite program with an empty linear context. With the type definitions in place, we can then use a technique that we have developed called Judgemental embedding to encode custom typing rules of session types as functions on the host language Rust. On the top, we have the typing rule of receive value, which updates the session type from A in the premise to tau right triangle A in the conclusion. The rule also introduced the variable A of type tau to the structural context in the premise. To encode this typing rule as Rust function, we first encode the premise as an argument to our function. Following that, the conclusion is encoded as the return type of the Rust function. To introduce new variable into the structural context, we rely on passing a continuation closure that accepts a Rust value of type T and returns the continuation partial session angle bracket C, A. Using the judgmental embedding technique, when we construct a partial session Rust value, we are essentially building a proof tree that follows the typing rules that we have defined in Rust. There are many details that we have not covered here on the encoding of each typing rule. However, the general principle of encoding typing rules as generic functions remain the same. To evaluate the feasibility of using Ferrite for real-world application, we have performed a re-implementation of the communication layer of the canvas component in Servo to use Ferrite session types instead of Rust channels for communication. Our modification to the codebase is relatively small, taking roughly 700 lines of changes out of the 300,000 lines of Rust code in Servo. We have a simple demo here that showcases the motion mark benchmark. first running on Firefox, and then have the same benchmark on our version of Servo that uses Ferrite. As we can see on the web page, the motion mark benchmark performs some canvas operations and shows the resulting frame rate. In the case of Firefox, the benchmark runs at roughly 38 frames per second. We can also run the same benchmark on Servo on the terminal window that I have prepared. As we can see, although the resulting frame rate is visibly slower, the performance is actually the same as the original version of Servo, which is roughly 11 frames per second. The full details of our implementation of Servo and the full benchmark result is available on our technical report, which we have published on arXiv. There are also a lot more information that we have not covered in this presentation, such as the use of context lenses to access and update channels in the linear context, higher order channels, recursive and shared session types, and n-ary choices. Do read our paper and check out the project GitHub page to learn more about Ferrite. Thank you for listening. Okay. All right, that's all. Is there any questions?
Yeah, go ahead and it doesn't seem like we have too much people jumping in, talking over one another. So feel free to unmute and ask questions. And we have a few minutes. Well, very few until the scheduled break time. One question. Who's up?
I will have a question.
Yeah.
But I also saw Peter had his hand raised.
Oh, I didn't see that. Go ahead, Ralph. You're up now.
Okay. Yes, thanks for the presentation. That was very interesting. So if I understood correctly, you're using some clever type level hacks to encode this linear context.
Yeah.
Which basically means you don't care about the fact that Rust is a fine at all here, right? You could do this in any language. So is there any benefit you're getting out of doing this in Rust versus doing this in another language?
Oh, so there's still some benefits because like the continuation in Rust specifically is affine, which means that when you write the program, the compiler is still reasoning that you cannot use the variables more than once. So that rule out quite a lot of other invariants that cannot be enforced in languages like Haskell and OCaml. Does that make sense?
I guess so. I mean, I guess you're saying for the rest of the program, because the session type system is just affecting the session type logic, but there's also all the other actual business logic.
Yeah, that's right.
But you also mentioned the continuations. That's a good point. Also, I guess you could call them twice.
Yeah,
otherwise,
that's right.
Which would be
so
weird.
So there's still benefit, especially like in our implementation, it's common that you can move an object into the continuation closure, and you can guarantee that it won't be executed more than once.
Yeah, that sounds useful. Is there any unsafe code in this?
No. So we don't use unsafe code directly. So
that's nice.
Yeah.
All right. Well, thank you for the presentation, Soares, and thank you, Ralph, for the question. Anyone having further questions, please take them to the chat. And let's all break and come back in 4 minutes.